All right, so elasticity, the property of a material that causes it to return to its original shape. Elastic force always acts as a force that resists change. And so we have this law, we call it Hooke's law. Of course, it's named after Hooke, and you can look up the personal history on Hooke if you want to, but it's a law for ideal springs. And when we say ideal springs, an ideal spring is not something that doesn't really exist. There's no ideal true things in this world, right? So there's always things that are going to have material flaws. They're not going to quite follow the rules. We say that an ideal spring law is something that helps us to model how a spring will behave under certain conditions or under a certain range. So it's a good starting point. Really and truly, this is going to be like a first order equation, but a second order, third order, fourth order equation might better model certain materials. Okay, so just for ideal springs. And it governs the relationship between the restoration force, that is the force that is tending to bring the spring back to its original shape. And we got a picture of a spring there, just in case you didn't know what one looked like. This is a linear compression spring of the spring, and the amount of length that it has been distorted by. And you might have people throw out words like distortion magnitude, which just sounds very academic, but it means length that it has been distorted by. Distortion magnitude. All right, so I have a series of pictures here, and the pictures are meant to illustrate some springs that are hanging from a ceiling. In the classroom, I've got a spring that's also hanging from the ceiling. Ooh, right, and if you're in the room with me right now, then there's a spring with a couple masses hanging off the ceiling. Before I put the masses on the spring was just hanging kind of limp like this. We call this the undistorted stretch. There's the undistorted length. And so I'm going to label it x naught, x sub 0. X naught, the undisturbed length. So let's make a little note to ourselves. X naught is the rest length or we could say or undistorted length. And then there are going to be some people that say, why is he calling it x naught, not x sub 0? And really, I guess it comes into personal history. Like a lot of you people, you'll have teachers that are British, Australian, South African, whatever, and x sub 0 is called x naught. I mean, myself, my wife's Caribbean. She grew up having x naught, because that's what 0 is. So that's why I'm calling it x naught, because it's like drilled into my head that way. If you call it x0, it doesn't really matter. Anyway, if I hang an object off of that spring, like the spring that's hanging over my head right now, it might have started off with a length of x naught, but it gets distorted by the distortion magnitude delta x. So we could come back up here and we could label that distortion magnitude as delta x. And we would say, all right, well, this spring now has a length, I'll call it L, cursive L. Length. Fair enough. And people say, okay, well, what caused it to be distorted? Well, there's a mass hanging on the bottom of it, of course. And Fg is equal to mass times acceleration due to gravity. And people say, okay, well, what about the spring force, though? And it seems to me, and here this is kind of like not a true free body diagram. It's an illustration that I'm adding details onto. But if the mass is hanging at a steady height, it's not bouncing up and down, it's not accelerating one way or the other, then what would be true about the spring force, the restorative force? Yep. Yeah, equal magnitude. This is a statics problem, essentially. It's a static equilibrium problem where the spring force is restoring equilibrium to this mass. It's keeping it in balance, okay? So in this situation, call it a special case if we like, the magnitude of Fs would be the same as the magnitude of Fg at the special position that we call equilibrium. For a hanging spring mass system. Now, if I had a spring like this one, notice that the spring that was initially illustrated was this length, and let's just say that this is the same spring each time. This would be a spring that can be stretched and also compressed. You can always tell a spring that can be compressed because there's gaps between the coils, right? If you look at a lot of springs, there's no gaps between the coils. They can only be extended. This one happens to seem to go both ways. So if we're going to compress this thing, let's just like give ourselves like a little cartoon hand. This is like a hand with a mitten on it, just so that we don't have to challenge our artistic skills too much. And we say, all right, well, this hand must have compressed the spring, which means that if it started out at a length that was down here where this dotted line is indicating, and we're just carrying on from the original length, then this would still be x naught, the length that it started at, the undistorted length. But springs that can be distorted by compression would have a delta x that goes this way. So when we talk about delta x, we really are talking about a magnitude. We're talking about how much it was distorted by, okay? Not a positive delta x, not a negative delta x, just how much it got distorted by. And so we would have a new length that would be cursive L, only this time cursive L is going to be much shorter than the original. And in terms of a force diagram, it seems to me that this little mitten hand must have had an applied force that was upwards. And what direction was the spring force? James? Down. Must be down. In this case, spring force is going to, again, resist what you've done to try and distort the spring. It's always resisting, always working against. So this delta x is the distortion magnitude. L is the length after being distorted. So I can call it the length when distorted. And I said that there's compression springs and extension springs, and I want to just jot down like a few examples. So one example of a compression spring. What would a good compression spring be? Alex? Car suspension, sure. Car shocks, suspension. What would be another one? I know that there's like pneumatics and stuff like that and hydraulics involved in those things too, but there could be springs, right? What's another thing? Yep. Bed springs. Sure, if you have a spring-based bed. Anybody ever been on a pogo stick? You should ride a pogo stick. I don't know if you ride a pogo stick so much as drive a pogo stick. Maybe you don't. You experience a pogo stick, okay? So a pogo stick. And if you don't know what a pogo stick is, you're going to have to look that one up and find out more about the exciting things of life. An extension spring. What would be a good extension spring? Yep. No, I thought I saw a hand. Yep.
A trampoline spring?
Yeah, a trampoline spring. You're right. Now that's a hard one to picture if you'd never actually like done any maintenance or really looked under the flaps of a trampoline spring or a trampoline pad. But if you do look under a trampoline pad, you know, there's the trampoline and the pad that covers around the outer edge of the trampoline. But underneath of that pad, if you zoom in, there are a whole bunch of springs that have a hook usually on one end and a hook on the other end, and one hook hooks into the frame of the trampoline and the other one hooks into the mat that you jump on the trampoline. And normally there's no gaps in between the coils of the spring, but when you jump on it, gaps open up, which is of course why the pad has to be there, because otherwise, I mean, I had a trampoline in my backyard as a kid, and I can remember people's legs slipping through the gap every once in a while, and one time this girl pinched her leg in the open spring coils, and boy, it left a mark, right? And I would have friends over and we'd jump on the trampoline. It was fun. My sister actually used it more than I did. She could do all kinds of flips and things. But you got to watch those springs. So there are trampolines now that don't use that kind of spring. They have sort of like an interesting underneath design. And I understand the people that hold that patent made a lot of money. That's kind of cool. Anyway, what's another one that's an extension spring? There's a popular one that rhymes with Winky. Slinky, yeah. Slinky, which is probably trademarked as a name. So, walking stair spring. Okay? Alone or in pair spring. Other ones that you might not think about depending on the design of your home, a screen door closer. And one that we're going to sort of reference, it's not truly a spring, but it's an elastic material that's an extension elastic material, is a bungee cord. Again, not a true spring, because I would think that most bungee cords would use polymers woven into a rope form, but this is going to be a material that has a stretchy quality to it.
This interruption, those students that are participating in grade games today, could they please be dismissed? So once again, any students that are participating in grade games, please make your way to the field. And also staff, any students that are participating should have an X beside their name.